to it. All right, I think this is gonna work out kind of good for us. So today we're gonna pick up with endochondral ossification. The last time we were talking about ossification in utero, right? So this was intramembranous ossification. You have this, these bones that spontaneously generate out of membranes, right? Our skull bones and other flat bones in our body. Endochondral ossification is another way that bones develop in utero. Right? In this way, bones are developing from a cartilage skeleton, right? So the fetus has a skeleton made of cartilage, right? And that cartilage slowly converts over to bones. That's endochondral ossification. This is almost all of our bones develop in this way, except our skull bones, as we've talked about before, right? So it occurs using the hyaline cartilage model that's already present, right? So embryo fertilized, right, divides into this ball of cells. A bunch of cells start growing into different organs, right, different parts of the body, and then slowly in these different parts of the body, there is a hyaline cartilage outline of where the bones will be. Endochondral ossification tells us that those pieces of hyaline cartilage eventually convert over into hard bone. So it begins at something called a primary ossification center, and then continues at something called a secondary ossification center. So if you imagine a long bone, our long bone will have primary ossification centers and secondary ossification centers. These centers eventually grow together. If this is all cartilage, the beginning of endochondral ossification is going to start in, it says, bone begins to form where osteoblasts have built an external bone collar. So it kind of starts on one little snippet, one little piece of the outside of the bone, or outside of the cartilage, begins to turn to bone. These chondrocytes here, for whatever reason, switch and start differentiating into osteoblasts, right? And these osteoblasts start laying down bone matrix. And this, it's kind of like dominoes, right? It starts in one area and then it just keeps spreading to other areas. And that's how this ossification happens. It continues up into the medullary cavities. It continues down into the epiphyses until eventually you have a cartilage model that is now completely ossified, completely turned to bone. So this is what it's going to look like, right? The outer edge, right, which is surrounded by a perichondrium. That's the cartilage blanket that surrounds the hyaline cartilage. That perichondrium begins to differentiate into periosteum. Again, the cells just kind of say, whoop, we're going to start doing this, right? It has to do with gene regulation. The genes turn on and off. The genes that make them cartilage cells turn off. The genes that make them bone cells turn on, right? And that turning on of those genes allows them to start ossifying that area. And that ossification just kind of spreads like a virus, right? Just kind of spreads throughout. And more cells will start differentiating. This happens in the same fashion that we had before, right? So here we have osteoblasts coming along, laying down calcified matrix, and turning into osteocytes. It's that same flow chart that we drew in the last class, but here it's happening from a cartilage model. So it's the same idea. The cavities that are being created and filled with bone, they eventually spread until they meet each other, and the entire thing is filled with bone. The epiphyses have something called the secondary ossification center. So the primary ossification center will start along the diaphysis, and the epiphyses have the secondary ossification center. And really, the piece of cartilage that's in here doesn't solidify until after puberty. The piece of cartilage, that piece of hyaline cartilage that's here at that epiphyseal plate where the epiphysis and the diaphysis meet up, that does not seal and become ossified until after you stop growing, right? That's that growth plate. It's a remnant of when your bones were undergoing endochondral ossification in utero and forming this osseous tissue. So everything else becomes ossified. The medullary cavity keeps becoming enlarged by osteoclasts. The osteoclasts that are in there just keep dissolving and chipping away at that inner cavity, redepositing it on the outside of the bone so the bones can get thicker and wider and stronger. So eventually, nutrients can come in where that original bone collar was. Oops. Nutrients can come in where that original bone collar was. That's our main nutrient artery feeding our bone, right? And it spreads throughout.
So that becomes like the nutrient foramen?
Yeah, exactly. Yeah, and notice that that extra piece of cartilage remains, right? That's how longitudinal bone growth happens, you know, from a child till you're, 18, till you stop growing, right? So, and you can see, even on x-rays, that those growth plates are there on long bones. On adults, so for all of us, it would look like a line, but on children, or people who are still growing, it literally looks like a joint. Sometimes it literally looks like two separate bones next to each other, depending on how the x-ray is angled. So, and of course the articular cartilage remains on the ends of the bones. So even after endochondral ossification, you have the articular cartilage on the ends, and you have that epiphyseal plate between the epiphysis and the diaphysis, right? That's going to remain. I can draw it in. These markers are, I meant to bring new markers. Kind of cruddy. This is just the remaining, or this is just the remaining cartilage after endochondral ossification takes place. So let's talk about some diseases and disorders that are associated with our skeletal system. First one, osteoporosis. Osteoporosis is the most common bone disease in the United States. This is where the bone matrix becomes weak and brittle. So basically what happens is we have this normal bone. This is the spongy bone, right? We can see all those trabeculae in there. The osteoclasts are in overdrive. They're taking away the calcium matrix, dissolving it, sticking the calcium into the blood. And so what you have left is this porous, uncalcified or decalcified matrix, right? And this is going to make the bones very, very brittle. So this happens because of diet, not bringing enough in, not bringing enough vitamin D in. Vitamin D helps with calcium absorption. Even if you don't drink milk on a daily basis, as long as you have a nice balanced diet, maybe eating some cheese and yogurt every couple of days, you're bringing in enough calcium. But if you don't have the vitamin D to absorb the calcium, it's not actually going from your digestive tract into your blood. So you need to have the vitamin D and the calcium, right? Females are more likely to have this because of our hormones. Hormones play a role. Exercise can affect this also. People who exercise more are less likely to have osteoporosis because of that concept of you don't use it, you lose it, right? If you exercise a lot, you put lots of stress on your bones, they're going to grow big and strong, which is going to make them less likely to be weakened by osteoporosis. There's also genetic factors that play a role in osteoporosis. Having a lack of calcium and vitamin D, obviously that's also going to increase your risk factor for bone breaks and fractures, which we'll talk about in a little bit. So, yeah, osteoporosis. They diagnose it through a bone density measurement. So it's a scan. It's not. They don't even have to. You literally just like stand on a thing, and they can like send the waves through you and detect the density of your bones in that respect. So it's pretty cool. Preventing with a balanced diet and exercise. Weight-bearing exercise. So walking's good, but actually using weights and doing something to actually build a sweat is much better than just the low-impact stuff. There are some drugs out there on the market. I forget what they're called. They're advertised just like any other drug. But what they do and how they work is they inhibit the osteoclasts, right? So they're turning those osteoclasts off so they're not dissolving the bone anymore. That makes sense, right? So. Let's talk about how our bones grow in length. We've talked about how they grow from the fetal skeleton, right? Intramembranous and endochondral ossification. But they grow in length in something called longitudinal growth. And this longitudinal growth happens at that epiphyseal plate, happens at that growth plate. So it's actually a joint in between technically two bones. The epiphysis of one bone and the diaphysis of the same bone, right? and that cartilage there stays, and new bone cells are kind of grown in this general area. Some are grown on this side and some are grown on this side. So osteoblasts, that same flow chart that we drew last time, right? You have your osteogenitor cells, those stem cells, differentiate into osteoblasts, and osteoblasts kind of hoard the calcium around themselves until they're osteocytes. That's happening all around this epiphyseal plate, right? And that's causing the longitudinal growth. So there's two locations or two places of significance on the epiphyseal plate. There's a reserve cartilage place, and then there's something called the zone of proliferation. So the zone of proliferation is where those active cells are dividing. Those cells are actually dividing and growing, right? The zone of reserve, these are ones that aren't really involved in the actual growth process. These are there kind of as a backup plan, right? Hence the zone of reserve. They're there set off to the side, living in the cartilage itself. They can be called up to be turned into bone cells if they need to be, but more than likely they're just going to sit there. Wrong way. All right. The zone of hypertrophy, right? Hypertrophy means growth, so this is where lots of growth is occurring. The zone of calcification is where calcification is happening, and the zone of ossification is where all of those calcified chondrocytes and osteoblasts live and become surrounded by the calcium. Right. So remember, calcification is just depositing the calcium. Ossification is taking that calcium, right, and packing it around bone cells, right, to form those osteons that we mentioned in the last lecture. So you have a zone where these mature chondrocytes or mature cartilage cells are growing, and they're like, pick me, I want to be a bone cell, right? That's what they're doing. And then eventually, some of them are recruited and calcified, kind of turned to stone, if you will, right? The calcium kind of grows around them, and then eventually those cells become the osteoblasts and osteocytes that are in bone. So this is just the micrograph view of the epiphysis itself. So there's a lot going on, and what's happening is these cartilage cells, these chondrocytes, right, are being recruited and surrounded with calcium and turned into osteoblasts. Oops, wrong way. Okay. Chondrocytes will divide in that proliferative zone. They enlarge. As they enlarge, the little nest where they live, the lacuna, gets larger as well, and that's when they stop dividing. They'll actually stop dividing, and that's kind of like they plant their roots. This is where I'm going to live. I'm going to live in this spot right here. So, calcified cartilage is replaced with bone, right? So once that cartilage has rooted in place, it's surrounded by calcium. It's been calcified, right? Now, the next step is for osteoblasts to invade. Right, so osteoblasts are coming down from that bone tissue, and osteoblasts are going to take over that lacuna. Osteoblasts are going to kick out the dead chondrocyte. They're going to move in. They're going to take over that little nest. So the rate's pretty slow, right? So in the beginning of youth, right, growth happens pretty quickly. If you've ever looked at, and I'm sure at home somewhere, there's maybe like a door or a door jamb that has like your heights over time, and you know, you can look back and be like, oh, this year I was this tall, and this year I'm this tall, right? See your growth rates there. Well, the actual closing of this plate, right, once you're ready, it's ready to close, right, after puberty, it's a fairly slow process. So it starts right around the age of 12, right? And if you think back to your own life, think about, when did you get to the height that you are, right? When did you get to the height that you are? Some of you, it could have been maybe 4th or 5th grade, and some of you might not have been until high school, right? I'm trying to think for me. I think I was in high school. I was probably 9th grade maybe. when I was as tall as I am now. So, and that varies based on genetics and hormones and things like that. And right at that point, when you get to right about where you're going to be, that's when this epiphyseal plate begins to seal up, and the whole thing gets converted into bone. And so that generally happens between the ages of 18 and 21. It's a pretty slow process, and now we call that epiphyseal plate an epiphyseal line. Right? So this shows up on x-rays as a little calcified line across your bone. So here it is. If all of that was like a lot of words, you're like, I don't understand. It's right here in a flow chart. I didn't draw it out, again, because the markers that are in here today are really, really weak, so I'm using them sparingly, but it's right here. So our chondrocytes, oh, thank you. Well, this is here, but next time I'll grab them, thank you. So chondrocytes divide, right? Chondrocytes reach that next zone, they kind of get pushed up, kind of like in the layers of skin, right? They're starting to divide and then they get pushed up, right? They're trying to make their way to that border where the bone is, right? They get pushed up into that hypertrophy zone, then they start to be calcified. Once they're calcified, they don't have a blood supply anymore, so they're totally cut off, right? And now they're slowly replaced with osteoblasts. So, bones don't only grow in length, but they also grow in width. When they grow in width, it's called oppositional growth. Opposition with an A. It's like appositional growth, but I say oppositional growth. Oppositional growth. Osteoblasts in between the periosteum and that outer bone surface is where this action happens. So these cells, the cells that are actually going to make your bones grow wider and thicker, are actually cells that are located on the very outside of your bone. So if I was holding a bone here, the bone cells that I'm touching are the ones that are going to actually divide and create new rings, so to speak, around the entire bone for this oppositional growth. So what is formed are something called circumferential lamellae. So what you'll have in a cross section, I'll see how good these work up here. You're sure they're not permanent? Oh, great, erase bold, okay. That would be horrible if I wrote up here with Sharpies or something. So, let's see. In a cross section of bone, we have all of these osteons, right? Right, so these are all the osteons. Woo, these are smelly. No wonder you're always smiling every day. All right, so, and then around these osteons, if this is a cross section of bone, is something called circumferential lamella. Circumferential lamella. These are the lamella that go around the entire bone. Circumferential lamella. On top of the circumferential lamella are, or is, the periosteum, right? This periosteum, this bone blanket that wraps everything up. The periosteum. So when we're talking about oppositional growth, we're talking about cells that are on the inner lining of this periosteum laying down another ring, right? Laying down another ring that goes around the entire width of the bone. So bone growth is going to occur in diameter, right? This bone is going to get wider because another ring is going to be added in between the periosteum and the bone surface. Let's talk about another disorder called Achondroplasia. This is a disorder that affects oppositional bone growth, sometimes called dwarfism. Achondroplasia is caused by defective genes where the growth factor affects, there's a mutated growth factor that affects your cartilage. And so what ends up happening is the bones grow abnormally and that epiphyseal plate closes early. So if that plate closes early, the bones can't grow long, but they can grow wide, right? So if you look at someone that has achondroplasia, their limbs are short, right? Their long bones, which should normally be long, are shorter, but they're still very thick. The bones are still very thick. And so this creates long-term problems with them. Obviously, living a shorter life is difficult, driving and things like that. But also, there's lots of joint problems associated with it because their bones are so bulky. on the ends because of all this extra oppositional growth that's going on instead of the longitudinal growth. Make it bigger. How do I make it bigger from here? Resume slideshow. Okay. All right. So there's lots of hormones that play a role in all of this. So the gene mutation in the cartilage for achondroplasia, that's one way bone growth can be affected. But we have lots of hormones that are going to play a role in this also. We briefly mentioned estrogen when we talked about osteoporosis, but there's some other ones in there. Growth hormone is one of the major hormones that plays a role not just in your actual growth, like growing, but growth hormone plays a role in all of your metabolic processes. So anything that's related to growth, right? How your cells use energy, growth hormone is in charge of that. So protein synthesis, all of these things, making new hair, making new skin, making new nails, growth hormone is affected by that. So growth hormone affects both longitudinal and oppositional bone growth, the lengthening and thickening of the bones. Right? It's going to increase the activity of osteogenic cells, those stem cells that can create new bone cells. When growth hormone's there, it can activate those osteogenic cells to create new osteoblasts. And we know what osteoblasts do, right? They build bone. They're going to start that calcification process and build more bone. Testosterone, the male sex hormone. Even females have testosterone in them, various concentrations. It varies throughout all of our lifetimes. But this is going to increase oppositional growth also. Think about it. Most guys, compared to most girls, and again, this is such a generalization, but they have, bless you, thicker bones, right? They have broader bones. Why? Because of testosterone. Testosterone makes males' bones bigger than female bones. It increases the rate of mitosis at that epiphyseal plate. It's going to make them grow faster, right? That's those growth spurts, right, that happen. Maybe, I remember there was a couple kids I went to school with, you know, like in 6th grade, they're like this puny little thing, and then they come back in 7th grade, you're like, hey, right, you grew up over the summer, right? Those things. That's that growth spurt, right? That's that increase of testosterone causing that. It also accelerates the closure of the epiphyseal plate. So it does the opposite, right? Where it's once you grow, and then you're done. Right? Estrogen plays a little different role. Estrogen is going to increase the rate of longitudinal growth, but it actually inhibits osteoclast activity, which is why having low estrogen levels later in life is linked to osteoporosis, right? Because that estrogen is actually inhibiting osteoclast activity. But after menopause and your ovaries aren't releasing estrogen anymore, wah, wah, right? So when estrogen levels spike, that's when the growth spurt occurs in the females, right? It can also accelerate the epiphyseal plate to close much faster than the testosterone, which is another reason usually girls kind of spurt up faster and earlier. You know, the girls might, on average, grow when they're in 6th and 7th grade, and then the boys kind of grow when they're in 8th or 9th grade. You know, just again in general. Having excess growth hormone though can be a bad thing. So it can produce two conditions. In childhood, it can produce a condition called gigantism, which is where the epiphyseal growth plates they don't close, right? So the individual gets very, very, very tall, very, very fast, very long limbs, very tall, right? This is like, you know, the people, like the tallest man in the world, what was he, like 8'12" or something like that, right? That's gigantism, right? Some of the basketball players, I don't know anybody's name, but some of them they clearly have some type of hormone imbalance because of just how tall they are. So gigantism is just that extra little piece. Acromegaly, this is when growth occurs after the plates have closed. So acromegaly, you're not going to get taller, but this is kind of like achondroplasia where the bones get thicker and broader. So people with acromegaly generally have really broad facial bones, maybe a really long, broad jaw, maybe really big hands, and all of these have their side effects. So like acromegaly, for example, your heart and kidney can be affected by those changes. Is that it? Yeah, okay. So let's talk about bone remodeling and homeostasis. So we mentioned bone remodeling last time, this process of continually kind of sculpting. I think of bone remodeling as kind of like the ongoing plastic surgery of your bones, right? Nipping and tucking all the time. Taking some from here, sticking it here, right? Always. That's what our bone remodeling does. It's a cycle of bone deposition and bone reabsorption, right? Reabsorbing that bone that isn't being used and or depositing more on bones that are being used. So this is maintained during calcium ion homeostasis, right? If your calcium ions are being maintained by your diet and other factors, bone remodeling can occur very well. Replacement of primary bone with secondary bone as the endochondral and intramembranous ossifications occurring. This can also help with bone repair, replacing old brittle bones with newer bones, as well as adaptation to tension and stress, right? If you've lived a sedentary lifestyle and all of a sudden you decide you're going to be a CrossFitter, your bones need to adjust, right, to all of that stress and pressure of picking things up and putting them down, right? So, all right. So in healthy adults, this process of bone remodeling occurs all the time. It's happening right now, and it's happening. The deposition and resorption is happening constantly, and it should be happening at the same rate, right? So you should have bone deposition going on in certain areas of your bones that are being used a lot, and then bone resorption going on in areas of your bones that aren't being used as much, right? In childhood, the deposition is taking place at a much faster rate, which is how children are able to grow, right? This is also why they're hungry all the time, because they need that energy so that they can grow, right? And so once we get closer to adulthood and once we're done growing, the rates of deposition and resorption are just about equal. So in bone reabsorption, what's happening? Last time we just mentioned osteoclasts. We said that, they dissolve bone. What they're actually doing is they're actually secreting hydrogen ions. When you think of hydrogen ions, you should think acid, right? They're literally secreting acids onto your bones, right? These osteoclasts are secreting acids, and those acids will actually dissolve the calcium, right? We mentioned what would happen if you took like a chicken wing bone or any bone and sat it in an acid like vinegar for a day or so. All you would have left is a bunch of collagen. That bone would be very flexible, right? And so this is how your osteoclasts work. They literally dissolve the calcium, and the calcium ions become liberated or freed, and then they go into your blood. They can go wherever else, right? And so that's what bone reabsorption is. Or bone reabsorption is then the osteoblast can take those cells, take the calcium rather, not the cells, take the calcium and stick it on to wherever else the bone needs, right? For whatever part of the body, whatever part of the body that needs that extra calcium, whatever part needs to grow. So it happens in response to tension and stress. That's the one that really applies to our lives because we're all done growing in here, right? So compression, tension, and pressure are all going to feed this process of remodeling, right? Think about the bones that we're looking at in lab. We've really only looked at the skull so far, but there are processes that stick off of our skull. Think about if you can picture the mastoid process, that big mountain, right? That's right kind of at the back corners of our head right there. We have some really big neck muscles that attach to that, right? So if you have a job, or maybe for fun, you love to turn your neck, right? Or maybe you do neck exercises or something like that, where you're using these neck muscles a lot. Well, guess what? That mastoid process is going to be a lot bigger and a lot thicker than on someone that doesn't do those same types of exercises. I'm using the mastoid process because we haven't really talked about the arm and leg processes yet. Those would make a lot more sense to use this analogy with, but hopefully you understand, right? The more your muscles pull on those things, the bigger and stronger they're going to get. And that's why they're there, right? They kind of serve as an anchoring point for those muscles to attach. So pulling on the bones more is only going to say, hey, we need more bone here because we're pulling away, right? We keep contracting this muscle. We need more bone mass here. And that's what this remodeling process is all about. The remodeling process is also about reshaping your bones after a fracture. How many of you have broken a bone before? Oh, good, a bunch of you. Okay, so we can share bone break stories one day, but after you break a bone, even years after, I can still feel where that bone was broken, right? So the remodeling continues after that break, right? My little osteoclasts are taking some of the extra bone and depositing it in different places to create a new shape for my bone. They never really go back 100%, right? Hormones can play a role in remodeling. Age can play a role in remodeling. Because with everything, with age, our hormone levels decline, right? Metabolism declines. So your body's not going to be able to remodel as effectively the older you get as it did when you were younger. Your calcium ion intake is really important for this, as well as your vitamin D intake, right? We mentioned calcium and vitamin D are necessities. You have to have both. So you also need vitamin C for your bones. Vitamin C is important for collagen. If you don't have vitamin C, you won't have enough collagen. And as we know, collagen is one of the major components of our bones. So you need your vitamin C. You also need vitamin K. You need vitamin K to help with calcium. Vitamin K and calcium go together well to help these osteoblasts build these calcium salts. And of course, you have to have protein, right? Proteins have amino acids in them. That's going to help you build the collagen also. So let's talk about calcium ion homeostasis. So if there was any of these things that are in our control, other than our exercise, right, and the amount of tension and compression that we're putting on our bones, it's how much calcium we're putting in our body, right? You can control your diet. You can choose to eat calcium or not. So there are two main calcium ions, or let me back up. There are two main hormones that balance calcium ions in your body, right? Calcium ions have to be closely monitored because calcium is such an important ion. Not only is it stored in our bone and makes our bones hard, right? But we need calcium for muscles to contract. You need it for your heart to contract. You need it for nerve impulses to be sent from one neuron to another. And you need it for blood clotting. You'll see you need calcium in every single body system. From here on, we'll be talking about calcium, right? And our body's store for calcium is our bones. So it's kind of like, man, I ran out of bread. All right, I got to go to the store and get some bread, right? Your blood runs out of calcium. Where's it going to go? To your bones, right? So it's really important to keep a lot of calcium in your blood so that it can be used for all of these things. So we're going to look at how that happens. It's through a negative feedback loop, right? The two hormones involved, one's called parathyroid hormone, the other one's called calcitonin. I think I'm just going to draw a little flow chart over here, and then the PowerPoint will kind of catch up with us. So let's say for whatever reason you haven't been eating enough calcium, or maybe you're exercising a lot, but your diet's not keeping up. So you're depositing a lot of calcium on your bones, but there's not a lot of calcium in your blood for that reason. So your blood levels of calcium drop. So when calcium blood levels drop, your body says, uh-oh, how's our heart going to beat? Uh-oh, how's our blood going to clot? We need a constant level of calcium in our blood. So the hormone, parathyroid hormone, is released. The parathyroid hormone is going to raise blood calcium levels. It does this in a couple of ways. The parathyroid hormone is going to increase osteoclast activity. Remember what osteoclasts do, right? They dissolve bone, right? They take the calcium out of the bone and stick it in the blood. Parathyroid hormone is the thing that makes them do that. So increase osteoclast activity. Parathyroid hormone is also going to increase calcium absorption from the digestive tract. And parathyroid hormone is also going to increase calcium reabsorption in the kidneys. So basically saying, hey kidneys, please don't pee out my calcium, I need it. right? So all of these things are going to raise blood calcium levels. Which is awesome. But sometimes our blood calcium levels get too high, right? And just like anything in homeostasis, we have to maintain equilibrium. We have to get back to that number, that concentration that your body likes to be at. So if your calcium levels get too high, we have to have a way of bringing them back down, right? Say you just drink a cup of milk. Maybe you ate a cup of yogurt. Maybe you just ate a whole block of cheese. Sometimes I do it, don't judge, right? So for whatever reason, you get a lot of calcium rushing into your blood. Now, our calcium levels go too high. There's another hormone called calcitonin, which is released. Parathyroid hormone comes from a small gland called the parathyroid gland. The parathyroid gland is actually located on the back of your thyroid gland. Remember your thyroid gland, this little fatty butterfly like in this area? Well, if you were to peel it off and look on the back of it, that's where your parathyroid gland is. Oh, right there. There you go. Your thyroid gland is that big butterfly, right? And that is the thing that releases calcitonin. Calcitonin does the opposite of parathyroid, right? So they're literally opponents here. So calcitonin is released. So what's going to happen? We don't have an increase in osteoclast activity. We have an increase in osteoblast activity. Yeah. We don't have an increased calcium absorption from the digestive tract. We have an increase, or we could just say we have a decrease in calcium absorption. In other words, you're getting rid of it, right? You have an increased elimination. And you also have a decreased reabsorption. At the kidneys. So you have a decreased reabsorption, or you can say an increased secretion. You're going to secrete it. You're going to get rid of it in your urine, right? So all of these things are going to lower blood calcium levels. So if we think about this in terms of homeostasis, right, the stimulus is our calcium level, right? The receptor, in the case of low blood calcium levels, is our parathyroid gland, right? The control center and the effector are the parathyroid hormone, right? The parathyroid hormone is going to go out, and it's going to negate that stimulus, right? It's going to turn off that low calcium level, and it's going to affect there it goes again, osteoclast, the kidneys, and the intestines. Reabsorption being increased in the kidneys and the intestines, and osteoclast being activated. So this is the flow chart. In case you can't read what I did, or if it doesn't make sense, it's all right here, right? Calcitonin is the opposite, right? Calcitonin comes from the thyroid. It's going to do bone deposition, so it's pulling calcium out of the blood. And so, in summary, all the things that are going to affect remodeling, right? The amount of tension and stress, all of our hormone levels, not just testosterone, growth hormone, and estrogen, but also calcitonin and PTH, right? Exercise, all of these things. Our osteoclast and osteoblast activity are affected by many things. Let's talk about fractures. So, fractures can be simple and compound. Has anyone had a compound fracture? What was it? Tell us. You don't have to. I'm just kidding.
No, I broke my leg in 2 spots, and they basically had to go in and put a steel plate.
Oh, it was sticking out of your leg?
A little bit.
Oh.
So they had to go in surgery.
Was it your femur?
No, it was right down here by my ankle.
Oh, okay, so that was your fibula.
Yeah, I have a nice big scar.
Oh,
I still have
cool.
8 the screws. I have
Nice.
one screw like that big.
Nice.
Goes straight up.
Do you know how many screws you got?
9 screws and then a real big pin.
Nice.
So 10.
Cool. Okay, I have 10 screws, but I only have a plate. I don't have a rod.
Also broke my jaw.
Really?
Yeah.
Did someone knock you out?
No, I was in a car wreck.
Oh.
And I broke my jaw, both clavicle and my cheekbone.
Whoa.
And my nose. My nose has been broken.
In my other class, there was a girl that was walking. She was a pedestrian. She got hit by a car, and that's how she broke her bone. So a compound fracture is one that sticks out of the skin. Ooh, right? I worked at University of Maryland College Park. I worked at the gym there. It's a huge gym. It's like the size of the arena club, if not bigger. And so I was a supervisor, so I was like in charge of like monitoring like the basketball courts and the tennis courts and the squash and the racquetball courts and the the weights and all that stuff. And you know where the most injuries occurred?
The weights?
The squash court. People that play squash were vicious. There was always broken ankles. Well, squash is kind of like racquetball. It's like this. It's just a smaller ball, like a smaller racket. Yes. Who would have thought? It's so dangerous. On every shift, man, I'm on the squash court again. So I'll tell you my bone break stories one day, but I got a couple of them, all fairly recent also. Let's talk about some of the different types of fractures. Whoops. This will zoom in. There we go. So they're usually named after how they happen or what happens to the bone when they happen. So a spiral fracture would happen in a twisting motion. And so generally you'll have some type of spiraling of the actual bone where it's broken will look spiraled. A compression fracture, these are most common in the vertebrae from compression forces. A lot of people that ride horses have bad backs from compression injuries, bobbing up and down. People that sit a lot have compression fractures. Comminuted fractures, this is a shattering. The bone's shattered into multiple pieces. And that usually is what happens when you need a plate and some screws and things like that, rods and stuff, putting it back together. An avulsion is when the tendon kind of pulls off of the bone. That's a pretty painful thing because tendons don't have a lot of vascularization. They take a long time to heal. Greenstick fractures, these happen a lot in children. So greenstick fractures are kind of like, have you ever broken a tree branch or a twig? Right? And it breaks on some of it, but then there's still like a little piece of it holding together. That's what a greenstick fracture is. So part of the bone breaks, but it doesn't break all the way through. So part of it's still together. So this one obviously is going to heal a lot quicker because it's still being held together. And then a growth plate fracture and epiphyseal plate fracture. Obviously this is only going to happen in children, right? Pretty common fracture. Could interfere with growth. So luckily, that periosteum, right, that bone blanket, unless you have a compound fracture that's poking out of your skin, that bone blanket holds your bones together enough that even if you didn't have surgery or have a cast, if you immobilize it enough, it would grow back together eventually. So if you're ever like stranded on a desert island and you break your leg, like it's okay. Just try to immobilize it and 8 to 12 weeks later you'll be fine. That's generally the healing time for most injuries. Okay, come on. There we go. So let's talk about how it happens. The first step is a hematoma. See, maybe this one's okay. Yeah, this is a good one. Hematoma. So a hematoma is basically a big blood clot. It's kind of like a big blood bubble that forms around the break, right? And that's so nutrients can get in there. It's also so all of the debris and pathogens, anything that doesn't belong there, broken things, like broken cells, can get swept out by the blood, right? Kind of keeping that area in a nice little, it sounds gross to think of a blood bubble, but blood's what cells need to get the oxygen and the nutrients so that they can grow. So it's a good thing, right? Then what's called a soft callus forms. A callus, right, like the callus that we get on our hands when you're driving too much or lifting weights, right, that hardened skin. It's the same type of thing, except here's a piece of your cartilage that kind of grows and forms over top of where this break is, right? And so it's made mostly of fibroblasts and chondrocytes. We have cartilage, right? And fibroblasts do what? what do? You remember?
It, you know,
They secrete fibers, right? They're like Spider-Man, like go web. So they're there to lay down all of the collagen, right? Remember, collagen's a huge component of our bones. So the chondroblasts are there to lay down new cartilage cells, right? So that will then eventually turn into bone. And the fibroblasts are there to lay down new collagen. Eventually, the osteoblasts will build a bony callus. And that bony callus can still exist. I know I can feel in my wrist exactly where it was broken because there's still a bump there, right? The bony callus is what you can still kind of feel on those broken parts. Eventually it goes away, but this was 4 years ago and I can still feel it. So this is the whole thing in picture form, right? Hematoma, big old blood clot, right? Chondroblasts lay down a nice chondrocyte callus. Then we have a bony callus, and then remodeling. Right? Remodeling is the very last step. That's going to continue to occur to rebuild and reshape the bone so that it gets back to as close to its original shape as it can.
Are teeth bones?
Teeth are bones, yep. They're covered by an extra layer of something called enamel. Yeah, so actually you do teeth in the digestive system in 2 of 4. Yeah, but enamel is the hardest substance in the, is that it?
that's it.
Yeah. Oh, really? Holy moly, cool. I'll stop recording. We can share bone break stories if you want. We can review for your exam. There's lots of things you can do.